In this video, I'm going to show you how to draw vector graphics like this using just an Arduino and a handful of resistors. Stay tuned. Hey, what's up? I'm Trevor Makes, and this is a project that I've been working on to put this old analog oscilloscope to good use. While it may be bulky, heavy, and frankly it was a budget model even in the 1970s, well, nothing else looks quite as good as a cathode ray tube. This is especially true in X-Y mode, a feature of oscilloscopes that plots X and Y control signals, essentially an electronic Etch-a-Sketch. My digital scope is great for simple X and Y plots like hysteresis or phase measurement. But for anything fancy, the limited memory and coarse sampling rate controls result in a not so great picture. With the cathode ray tube though, the phosphor coating on the glass is the display memory, and it leaves a perfect zero latency trace everywhere the beam touches. This makes an analog scope perfect for drawing vector graphics. But first, we'll need a way to generate the analog control signals. That is, not just on or off like a digital pin, but a whole range of voltages proportional to the X and Y positions on the screen. The default way to do analog output on an Arduino is to use the analog write function, which uses a trick called pulse width modulation, or PWM. This uses a regular digital pin that can only be set on or off, but by toggling it on and off rapidly with a timer, and by varying the ratio of the time that it stays high to low, it creates the illusion of an analog signal. PWM works great for LEDs and motors where the value doesn't need to change too quickly and the highs and lows can be averaged out. Vector graphics is just not one of these cases, since we need to be able to update the value extremely quickly and without any noise in order to create a stable picture. What we need is a fast digital to analog converter, or DAC. One of the simplest of these is a binary weighted DAC, which uses several digital outputs from the Arduino as bits and requires only a single resistor per bit. The resistors are chosen from a power of 2 sequence like 1, 2, 4, 8, and so on, with the smallest resistor at the most significant bit and the largest resistor at the least significant bit. To understand how this works, let's look at a simple example that uses just 2 bits. If both inputs are low, then the resistors are in parallel and act as a pull-down resistor to tie the output low. If both inputs are high, the resistors are still in parallel, but now they act as a pull-up resistor to tie the output high. It gets more interesting when one pin is high and the other is low. Now, the resistors are configured as a voltage divider. If the most significant bit is high and the least significant is low, then the larger resistor is on the bottom and the output is 2/3 of the high level. If the least significant bit is high, then the smaller resistor is on the bottom and the output is just 1/3 of the high level. The same idea extends to more bits. You just end up with different combinations of resistors in parallel and in series, making voltage dividers and so on. Now, I should point out that this type of DAC is very sensitive to output loading. An oscilloscope or voltmeter can be connected directly to the output, since their high impedance inputs mean very little current is going to be drawn from the circuit. On the other hand, a low impedance load like a 4-ohm speaker would totally overload the DAC and sag the output voltage to near zero. In that case, you would just need an amplifier or buffer stage to isolate the DAC from the load. While in theory, a binary weighted DAC should be simple, there's kind of a big problem. The power of 2 series that the resistors are chosen from maps really poorly to the power of 10 E series that parts like resistors are manufactured to. And consequently, if you take a given resistor and you double the value a few times, you'll quickly end up with a value that's either hard to find or maybe doesn't even exist. For this reason, it's far more common to build a DAC using an R2R resistor ladder, which uses twice as many resistors, but only the same 2 values R and 2R. This is just a fun project though, and I'm only building DACs up to 6 bits, so the binary weighted DAC is going to work just fine for this purpose. I picked the resistors from a cheap metal film resistor kit that includes E24 values at 1% tolerance. That is, all of the values start with one of these numbers, but multiplied by 10, 100, 1000, so on. Well, except for 11, 13, and 16, because those weren't included for some reason. So my idea was to start with 750, double that to 1500, double that to 3000, double that to 6000, well, okay, that's not quite 6,000, but close enough. double that to 12,000, and finally double that to 24,000. I could have used a pair of 12K resistors in parallel to make up the missing 6K, but I decided to just stick with it because it worked well enough, and I plan on building a better DAC later on anyway. Before wiring things up though, we'll need to figure out which microcontroller pins should be hooked up to the DAC. To control the DAC, we're going to need something a bit more advanced than Arduino's digital write. This function, along with digital read and pin mode, were lifted from an earlier project called wiring, and were designed to simplify things by mapping out a set of virtual pin numbers, specifically the ones that you can see printed on the Arduino circuit board. This way, programs written for different kinds of microcontrollers can just use the same virtual pin numbers, and the low-level details will get worked out by the software library. This abstraction comes with a significant overhead though, and on an Arduino Nano, it takes about 50 clock cycles, or about 3 microseconds. Now, in most cases, 3 microseconds is not really a big problem, so it seems a fair trade-off. However, for a vector graphics display, what we really want to do is set all of the DAC pins at exactly the same time. If we try to update the pins individually, then the delay between each pin will result in the analog value glitching around whenever several bits would otherwise flip at the same time. That's obviously not going to work. Fortunately, AVR microcontrollers have an instruction aptly named OUT that can not only set up to 8 pins at the same time, but it does so in a single clock cycle. If you're counting, that would be hundreds of times faster than a bunch of digital write calls would be. The pins just need to belong to the same GPIO port, and the Arduino Nano has 3 such ports named B, C, and D. Conveniently, the low 6 bits of ports B and C each map to 6 digital pins, Arduino pins 8 through 13 and 14 through 19. Surprisingly, it's actually quite easy to write to these ports from code. For example, to write 42 to port B, just type port B equals 42, same as any other variable, but the compiler recognizes this as an I/O register and it uses the OUT instruction instead of a store. So if we wire both of these ports B and C to each of our 6-bit DACs, then we can write the values out to them with a single instruction, and all of the pins will update at exactly the same time. No more glitching and a much faster refresh rate than before. Anyway, with the resistors and pins chosen, that gives a final schematic that looks like this. And here it is on the breadboard. I used jumpers to take B5 over to the other side of the board with the rest of port B, and then I tied all of the resistors to the bus strips on either side of the board. The scope probes attach to jumpers coming off of those bus strips, and the whole thing gets powered over a USB. Now that we've built the DACs and know how to control them from the Arduino, it's time to look at how to use them to actually draw a picture on the display. You might be familiar with how analog video works on old CRT televisions and monitors. These work by continually sweeping the dot across the screen left to right and top to bottom in a fixed raster pattern. These are synchronized to the video signal by irregular pulses that indicate when the row should start and when it should return back to the top of the display. With a vector display, like an oscilloscope in XY mode, there are no sync pulses and there is no fixed raster pattern. Instead, we just move the dot wherever we want, and that's where the picture will be. To render a bitmap image, where the pixels are stored left to right and top to bottom in memory, we can follow that same raster order, but instead of a smooth sweep left to right, we can instead jump from pixel to pixel and skip those that shouldn't be lit. This way, the intensity of the dot doesn't need to change at all. And instead, the brightness of the pixel can be adjusted by leaving the dot in place for longer before moving on to the next pixel. I originally did it this way because my digital scope doesn't have a way to turn the dot on or off. And I figured that this analog scope was the same, just kind of based on what the inputs were on the front panel. However, I since found the nondescript ZMod input that's hidden away on the back panel. With the ZMod input, I can adjust the intensity of the display, but it requires some additional amplifier circuitry. Now, I've seen some people use this ZMod input on analog scopes like this to straight up display analog video signals, just like it's a TV. And I'm definitely going to give that a try at some point because it looks totally awesome. But for now, I'm not going to use the ZMod and I'm just going to stick with X and Y adjustments only. Another approach to drawing graphics with a vector display is to instead have the beam directly trace out the lines and curves that make up a picture. One way to do this is with purely analog circuitry generating functions like ramps and sinusoids. For example, a pair of sine functions of varying phase and frequency create an interesting family of figures called Lissajous curves, except these sine functions aren't purely analog. They're being generated digitally and then converted to analog by the DAC. Now, the complication with doing vector graphics like this digitally is that all of the lines need to be broken down into all of the individual pixels that plot them out, since we can't just rely on an analog ramp function to do that for us. This is where a fast line drawing algorithm comes in handy. And an especially useful one for this purpose is Bressenham's line algorithm, because it doesn't require any multiplication or division, especially division, since division is very slow on microcontrollers. It does this by keeping track of an incremental error as it steps across the line. When it takes a step in the x direction, the error is decremented by the magnitude of the y component of the slope. Then, when it takes a step in the y direction, it increments the error by the x component of the slope. This way, it can determine whether to step in x or y depending on how positive or negative the error has become. Surprisingly, Bressenham's algorithm can even be extended to drawing circles by modifying the error function that it uses to determine when to increment x or y. And, as a result, this is much faster than trying to draw out a circle using individual sines and cosines, even though we more or less get a good sine and cosine approximation, as you can see on the XY channel. Now, here's an animation that puts both of those algorithms together using the line algorithm to draw the border, which you can see as these diagonal lines here, and then the circle algorithm to draw this bouncing ball, which I think it's pretty cool. You can see the bouncing ball here as the cosine wave and the sine wave here. Well, anyway, I've still got plenty of improvements to make, like adding a higher resolution DAC, adding blanking controls, maybe adding video input, things like that. But for now, I'm pretty happy with how it's come along. And I think it's really cool to show off how you can do something like this with an extremely simple circuit just using a handful of resistors. If you've got any ideas for a cool animation I could put on here, go ahead and leave a comment down below and I'll check it out. If you'd like to download the code and build it yourself, it's available on GitHub and the link is in the description down below. Anyway, I hope you enjoyed the video. Thanks for watching and I'll catch you next time. And it leaves a perfect zero latency trace everywhere the beam. Doing this shit again.